have measured the distance to the celestial dome by utilizing synchronized stereo astrophotography, and they have taken notice. I was told in no uncertain terms that we can punch through the dome and keep going forever, forever, and ever. Just incredible, folks. We are living in monumental times. This is just incredible. If you've been following my channel, you know we've been breaking new ground and unlocking the secrets of reality. In this presentation, I'm gonna show you how I increase the accuracy of my results by using a theodolite. Okay, so I'm down here at mile marker 6. After taking the astrophotos, I've returned with the theodolite to make accurate angular measurements. Measuring the angles directly increases the accuracy significantly. We will need these angles for calibration, as you'll see shortly. Both of the cameras were separated by about a mile, and they were pointed in the general direction of a tower on top of Mount Potosi, and that is our calibration target.
Whoa, there's my timer right there.
Both of the cameras were time synchronized and started at one location. Then I took one of the cameras in my car and drove it to the other location. After taking the photos, I marked this location for camera 1 by putting a rock inside that stump so I could find it the next day for further analysis.
You see that? I set my tripod. I zeroed it out right on that bottle.
After taking the astrophotos, I returned with the theodolite to measure the angles accurately. I have a 2 arcsecond theodolite, and at one of the locations I put up a rock and a bottle, as you can see here. And this is what I'm doing. I'm using a theodolite to measure angles B and C to a very high accuracy, and I'm using the calibration target, a tower on top of the mountain. After measuring the angles B and C, we can calculate A by using the formula you see there. So A would be 180 minus B minus C. Once the calibration angle is determined, we'll use it to align the cameras. In this case, we rotate camera 1 by that angle so that its optical axis is parallel to the other one. So now we have a parallel set of cameras properly aligned, and we're ready to measure the distance to the stars or to any other objects in the imagery, like airplanes and satellites. Triangulation is a common yet powerful technique to determine distance to a target. The range to which an object can be resolved is dependent on the separation of the cameras, called the baseline, and the angle accuracy that we have. As you can see in the diagram, the farther out the measurement, the larger the uncertainty. For my setup, I use 2 Sony Alpha cameras with identical lenses and sensors. So 50mm focal length, and the pixel pitch is 3.92 micrometers. And so the angular resolution given these parameters is 0.0000784 radians. And if we take that angle and plug it in the equation, d over a, where d is 1 mile, we get a range of about 12,000 miles. So the instrument is useless beyond that, you know. And as you can see you know, the closer you measure something, the more accurate it is, less uncertainty in the position. Um, so we can definitely improve the experiment, go farther out, separate the cameras by a larger distance. If we double D, then we can get to, 24, 25,000 miles. We can also increase the focal length of the lens, but they get more expensive, and also they're not fast lenses. So I've done a lot of thinking and calculating and looked at exposure times and lenses. There's a lot that I'm leaving out, but I didn't just, just go out and do this experiment. There was a lot of thought that was put into it.
with the mountain.
Here I've rotated over to the mountain after zeroing on that bottle, so it's about 72 degrees, etc. And you see in the image two towers. Two of them on the right are actually overlapped, and the lights are on the left one, as you probably saw in the images. Now, the theodolite is a really great instrument, 2 arcsecond resolution, and so this frees us from having to determine angle A based on the distance D and, maps. This is actually very accurate. This map illustrates why we're only seeing two towers in the images. From side 2 on the right, tower 2 and 3 are actually overlapped in the line of sight. So that's why only two appear. And we're focusing the theodolite on tower 1, and that's where the red lights, the beacon lights, are located that we'll use to align the images.
So here we go. I set up here. I zeroed it out. I'm aiming at the sign.
So now I'm measuring angle B, and I start by aligning to the mile marker, that green plaque you see there, and zeroing out the instrument, and then rotating to the mountain. And this is very critical. We have to get the angle just right, as you'll see next. Let's talk about accuracy. To gain a sense of what we're up against, 1 pixel is equivalent to 0.0000784 radians, which is equal to 16 arc seconds. And the theodolite has a resolution of 2 arc seconds. So we're doing really good. But when we align, okay, at 1 mile, 1 pixel is equivalent to about 5 inches, and this mile marker is about 6 inches. So we have good enough accuracy. Optically, I can align it within probably an inch at that distance. Now at 17 miles, 1 pixel is equivalent to about 7 feet. Okay, so as long as we stay, within a foot or so along the line of sight, we're not changing the angle alpha out there. The reason for this is illustrated in the lower left inset. Multiple triangles can share the same vertex, and so the surveying marker, this bottle, had to be moved out because there's bushes in the way. So that's why this was done. So that's okay. As long as we stay along the line of sight, we can still calculate the angle alpha prime, which is our calibration or alignment angle that we're after. And so I estimate that the marker positional accuracy is better than 0.1 pixels, as this figure illustrates.
Okay, so I rotated, and it's 256, 1645.
So after completing the measurements, I used the equations in the top left corner to calculate the angle A prime, which is the calibration angle. The calibration tower sits at an elevation of about 3.3 degrees, and it is A prime that is the calibration angle. Even though they're fairly close, that's pretty significant. So it's very simple to derive A prime from A. It's just A times cosine of the elevation angle. And I use the average between E1 and E2 since they're fairly close together and it doesn't make much difference. So there's the equations and there's the calibration angle. However, after I determined the calibration angle, I realized that I underestimated the angle slightly, and here's why.
Okay, so I had to come back because there was a little difference. So that's where the tripod was. I analyzed the nighttime image, and when I did the theodolite, I was here, and I lined it up. I put the bottle down there. Okay, my theodolite was about here, and it's in line right there. But there is a gap. There's a gap here of I don't know, 1, 2, 3, 4, 5.
So the calibration angle was underestimated slightly by about 0.004 of a degree. That's 6/7 times the angle for 1 pixel. And so the final values are shown there. 3.824, that's the final in radians, 0.066741 radians. And in terms of pixels, 851.3 pixels. And so we'll use this value together with the values derived from imagery to calculate the distance to the stars. Image processing is actually quite simple but somewhat tedious, so I've taken 30 exposures out of the 2 cameras, left and right. 1 through 8 were ruined as I was moving the camera to the location. So here I'm starting to process L09, left and right. So I copied it from the right over to the left. I'm naming the layer. We have to copy as new layer. And we'll change transparency, and the first step is to align. Notice the images are not quite aligned, plus they're slightly rotated. So I'm going to use the stars to align and register the images. That's important. We want to use the stars to really get it. Oop. It's a little bit too much. No, that's not good either. But anyway, we're going to work at it a little bit and get it aligned just right. And then we'll move it to, get the stars right on top of each other. So here's this red star, and I'm going to bring them together. It takes a while here. Let's see, boom, there we go. So the steps are fairly simple. We're going to align to the stars in the center, then we're going to align the calibration tower, and then we're just going to measure the pixel differences. So here we're going to try to be very precise. I'm going to shift the layer over. There we go, it's overlapping. Yeah, right there. Oh, right there, that's even better. And so as we zoom out, we're going to notice that not all the stars are aligned. In the center, they're aligned pretty good. And there's a reason why they're shifted. We can rotate a little bit more, and we can work at that. But when we zoom out and we look left and right, we see a glaring difference in the stars. And I'll have a chart to show you why that is. Because that needs to be taken into account. So now, step 2, we are going to align on the tower. Okay, so let's see, boom, right there. So now I'm going to zoom in and get this aligned probably within a pixel. That's the best we can do. And now I'm going to toggle left and right a little bit, just so I can visually assess when it's aligned
properly. And it's somewhat subjective. The best thing to do is to use a computer and have it, look for it. Ooh, right there. That looks excellent. Okay. No, that's getting out of sync. Going back. I'll go back one more. Is that the bit? Yeah, right there. I think that's it. Yeah, so that's the process of aligning. And after we align, we're ready to just measure the stars. So there's the two red ones. Now it's important to, toggle the layers to make sure we're not measuring the wrong stars. It can be confusing. However, we were told that the stars are at infinity, so they should be around 851 pixels, right? Because that's the calibration angle, so they're at infinity. But as I was measuring around, I started to get values around 847, 848, 847. And I thought, what in the world? You gotta be kidding me. Small difference, 3, 4 pixels, but it's a difference. And I thought, this is very interesting. So I decided to embark on a statistical study. I have, a number of images. There's a number of stars. So I started measuring across the start field and trying to be as precise as I could. And I started tabulating all the values. But before we get into those, let's have a look at a much easier example. We're going to measure the distance to an aircraft. So here's an example. We're going to measure the distance to the aircraft in the scenery. And there's a few airplanes that pass in front. And we can tell those are airplanes. They have strobe lights. So you see the strobe lights. Boom, boom, boom. Okay, so we're just going to take the pixel difference. I exported this image. Notice it's 6,000 by 4,000. I haven't changed it, shrunk it, or anything. So I'm doing this in Paint since you can see the pixel measurement. So about 250. So the first step is to calculate the pixel difference based on the calibration angle. So 851 minus 253 pixels equals the number you see there. The next step is simple. We'll convert the pixels to an angle. So 1 pixel is 0.0000784. We multiply that and we get our angle in radians. Since the angle is fairly small, I'm just going to use the small angle approximation. And then step C, we're ready to calculate the distance, d over the angle, which gives us 25.4 miles. Very simple. However, if we want to improve the accuracy, there's some things we can do. And it's mainly related to the direction in which we're viewing, because the baseline is changing. There is a skew angle, as this graphic illustrates. So the aircraft is skewed over about 9.2 degrees from the tower, and that's based on the pixels times the angle of 1 pixel converted to degrees. And then the tower is 17.55 degrees skewed relative to the road, and so we have to account for that. As you can see here, there's the 17.55 degrees relative to the normal of that road, basically the perpendicular line. And so that takes us to the tower, and then the aircraft is another 9 degrees beyond that. So the effect that has is it shortens the baseline. You see, D is the baseline along the road, and the red line D prime is along the viewing direction to the tower. So the actual distance is slightly closer, 22.7 miles. And I began to wonder where that airplane is going. It's so close to the mountain. And it's like, whoa, watch out, buddy. We know from the last video that Carol Lombard was killed right on the other side of that
tower, 70 some feet below the rim. Oh my God. So anyway, let's find out the direction that this aircraft is going. So I went to the next set of images, and the aircraft is now moved, and I did the same calculations, and now it's really close to that peak, and I get 22.1 miles. So let's have a look at a map. Here we go. So Las Vegas, zooming in. I was about right there. There's the road. Let's see. Let's turn it over. Yep, I just saw the road. Yes, we're somewhere over there. Right where that other small road intersects, somewhere over there. So let me just click measure distance and kind of eyeball the direction somewhat. There's the mountain right about there. The tower is right there. So we're gonna go out at some slight angle here. Actually, let's just measure it, and then I'll go. Is that the angle? So it was 22.7 or so. So anyway, the aircraft is somewhere around there. So let's put it all together now. Look at this graphic, all the information that we can extract. So two sightings of the aircraft at t equals 0 and t equals 30 seconds later. Okay, the two image sets that I analyzed. So I got a distance to the aircraft, and you know, based on the angles and where it's at, it's fairly approximate, right? I didn't spend too much time for accuracy in the horizontal here, but this is just to illustrate what we can do with the data. And we can get the velocity, you know. I measured on the ground 4.6 mile difference in 30 seconds, so it's about 552 miles per hour. And then the elevation, you know, 3.3 degrees. It was very close to the tower, maybe 3.354. And that comes out to about 6,900. The observation elevation is 3,100. So it's about 10,000, right? So this aircraft is flying at 10,000 flight level, which is not uncommon. And my guess is that it came from the airport there, and then it banked. It's a fairly common flight path. I used to fly years ago out to the range, the Nevada Test and Training Range, on the classified flights. And we would take off sometimes that way, go right towards the mountain, and then bank, and then go down, and then up over Pahrump all the way to the TTR, the Tonopah test range out there. I used to work on the electronic combat ranges. And I've also flown into Groom Lake quite a few times in the years I've spent on the range. So yeah, they just go up and turn over, you know. So now imagine Miss Lombard, man, oh man, you know, flying in the dark, the beacon lights are off, and if your heading is off a little bit, oh my God, you're gonna go right into the mountain, which is what happened to her, you know. Just feel so bad about that. She was such a lovely lady. So now that you've tasted the power of this analysis, let's have a look at the stars. So while I was measuring around and I started measuring the stars, I was expecting to be very close to 851, maybe 850, maybe 852. And I was blown away when I started measuring values around, you know, 8,449, 848, sometimes 847, you know. And I started wondering, like, what? It's a small difference. Obviously, we're aligning to the tower plus or minus 1 pixels, but I thought, you know, a pixel or two, maybe that's significant, maybe 3 pixels. I said, wow, I should pursue this. And I decided, since I have so many photos, to do a statistical analysis of all the stars. And so I spent a lot of time. I've only analyzed maybe about 9 or 10 images because it's very tedious. And I put all this data in a spreadsheet.
Yeah, so using statistics, we can actually, improve the measurements. Because here we're really measuring plus or minus 1 pixel, and it's so subjective. I'm just looking at it and kind of eyeballing it. So, but by doing this over and over, we can improve, as you'll see shortly. So I try to measure stars sort of in the center because there is a skew as we look left and right. The baseline changes and the stars, the distance between them begins to change relative to the alignment right in the center between the two towers. That's 0 degrees right there. And so if we go from the center of the baseline, um, you know, it's about 2 degrees to get to the tower on either side. So I try to stay in the center. That's where the stars are nice and crisp and centered, and because I kind of veered around a little bit plus or minus, that spread out the statistics a little bit. Look at the numbers down below. If we don't correct for the skew angle, and we're measuring a star closer to a tower, it's about 2 degrees, we're off by about 0.51 pixels, So, yeah, I kind of, measured within that range of, plus or minus 2 degrees or so. I looked at a lot of stars up and down as well. And that was the experiment, and when I put it all together, it just blew my mind. I entered all the data into a spreadsheet, and right away I started to realize as I was putting it in, I tried not to be biased. Initially I said, I'm just going to write down whatever I see. I'm not going to try to correct it, or, if it's off, it's off. And I started going, and right away just entering it, I said, wow, this thing is biased towards a lower number. Oh my God. And I did a histogram of the data, and then wham, 847.63 pixels average. And I calculated the standard deviation and the upper bounds based on 90% confidence interval. So these are standard statistical analysis. There is the equation. That 1.65 is associated with the 90% confidence interval, and then that's the standard deviation divided by the square root of the number of values. And so we get about 0.3 of a pixel, plus or minus 0.3 of a pixel. So this is the largest error. Our theodolite and surveying, that was the best. So here I have the calibration, 851.3, and the measured from there, the average basically. And there's a delta of pixel, 3.67. It's like, whoa, there's a small delta. And then I calculate the angle. I need the angle. So I multiply the delta value of 3.67 with the 0.0000784 radians per pixel to get that angle. That's the angle alpha, basically. Okay? And I also adjusted for the baseline. Okay? And yeah, let me put that in there so we have it. So angle, that's A prime. That is the angle now to the star, not to the tower, to a star. Okay, and there's the baseline, 17.55. Times 1.19. And now let's calculate the distance to the star. Let's make the text red because this is important. It's going to blow your mind away. Distance to the dome. Okay, so it's going to be the baseline, okay, divided by the angle. And wham! 3,943 miles, folks. That is incredibly close to the radius of the Earth, or so-called radius. This just blew my mind, folks. Unbelievable.
So it's really the distance to the dome, not to the stars. They cannot be that close. I'll say more about that later, but here is the summary. I added also the low, average, and high table right there, for 90% confidence interval. And there is the assumed Earth radius of 3959. And we only have a delta between my value and this so-called Earth radius of only 16 miles. That just blew my mind. So what's causing all this? Well, look at the inset. We have a divergent lens, and starlight travels in parallel light rays and then diverges out. And we have the camera 1 and 2. And our equations assume a straight line propagation. And so we see the virtual image of the stars that just happens to be at the radius of the Earth, or better said, the radius of the dome. Okay, there's a fine distinction there. Now, if we assume straight line propagation, it's very interesting to do some calculations. So here's the globe model. Okay, and let's assume we can actually get the same value by looking at a 0-degree elevation. Okay, then this produces about 2,788 mile altitude to the dome from around Bogota. It's actually slightly closer, so very interesting. And you can think about this some more. If we assume 0 degrees elevation at the observational location, it makes the math easier, right? We have a 90-degree angle right there because it's tangent to the surface. The distance r to the center, distance r up to the point on the surface. And so yeah, very interesting. Now the stars that I measured were somewhere around 5-degree elevation, and I'll try to repeat the experiment to see if there's variation with elevation. But that requires a different setup. Now in the flat Earth model, yeah, things don't really work out all that well. So we know, if you've been watching my channel, you know there's I advocate for refraction, and what we're observing is something that has to do with the curved space-time. And possibly the dome and layering. So it's a very fascinating thing to pursue. Anyway, thanks for watching, everyone. Make sure you leave me some comments and give me a thumbs up. Appreciate you all. God bless. What monumental times we live in. See you in the next video.